Example 3, so we have done 1 to 2 and this is number 3 lah. The following test results are obtained from a 3-phase 60 horsepower 2200 volts 6 pole 60 Hz square cage induction motor, and the starter is connected as star winding. Okay, so we have wires in the starter connected as star or Y lah, same thing. Sometimes you say Y or star, means same thing lah. This is a rated condition, everything rated for the motor. The motor has 60 horsepower rated, 2200 volts line to line voltage rated, and 6 Hz rated frequency. The no load test given by this data. From no load test, when we run our motor at no load test, that means we apply 2200 volt lah. We inject 2200 volts, and this frequency 60 Hz, this rated voltage and frequency, and this is line current that flow in the machine. This is a line current, okay? We have star connected stator. This is a line current. That means line current to phase current lah, because star, you know that. That means I line to I phase, because star. And input power, this is power consumed during no load test, which is 1600 watts. This is input power used to supply for rotational loss. Okay, this is data that we got from the no load test. Current, power, voltage. Okay, and then we do the second test, which is block auto test. We block the rotor, we lock the rotor cannot move. We increase voltage slowly up to 270 volts. So this 270 volt gives us line current of 25 ampere. So we know that this is rated current for the machine. But it's not mentioned there on the top. That means we know that this 225 amps actually is a rated machine current. Maximum current that can flow in the machine equal to 25 ampere. And frequency 15 Hz. Why? Because they said just now, right? If you check the note just now, because the power is more than 20 horsepower. Now our machine is 60 horsepower. That's why the frequency needs to be reduced to 1/4 of the frequency. That means frequency is 60 Hz. 1/4 equal to 15 Hz. Definitely this kind of machine we need inverter lah. Inverter block to deliver this kind of frequency. Without inverter, you cannot get this frequency. Again, the input power measured during block auto test equal to 9000 watt. And the last one, average DC resistance. This is the first test that they show, they did, which is measure the resistance of stator winding. So in this case, they say per phase stator equal to 2.8 ohms. Okay, number 8, determine the no-load rotational loss. What is no-load rotational loss? Then you need to find you need to check the no-load test. So from no-load test, we can find the stator copper loss, and we can find the rotational loss. Okay, let's go there. Okay, this is a no-load test. How much the power just now? 1600 watt. Total power. Okay. So we know that the I1 that flow in the stator, which is 4.5 amp, and this current will make the stator voltage, stator copper loss, or stator winding loss. So I squared R, R1 equal to, given there, 2.8 ohm. So I squared 4.5 squared multiplied by 2.8 multiplied by 3, because this total loss in the phase. That one is this total stator copper loss minus total power minus this one, that is this is 1/4 to 20 is a rotational loss for the machine. Okay, in order to find the rotational loss, you need to minus total power minus dengan losses in the stator winding. And this one, because 1600 is the total power. When you put the meter there, it gives you the total power consumed by the machine, not per phase, total power. Okay, so that gives us rotational loss. So we measure rotational loss during no-load test. What else we got there? So determine the no-load rotational loss. Done already lah. You just find the total power during no-load test minus stator copper loss. Determine determine the parameter IEEE recommended colon sikit. They ask us to find IEEE recommended sikit. That means you need to find the component for S1, S2, SM, and also R2. Okay, the machine node is connected as star. Okay, star mean star lah. Star mean voltan line current to line phase current. But the phase voltage equal to line voltage divided by Z3. So when you read the question, you need to be careful whether it's star connected or delta connected. So in this example, they say star connected. That means we have to divide by Z3 to get the phase voltage. So 220 ni, 2200 ni, divide by Z3, that give phase voltage. It is 1270.2. This is phase voltage for no load test. Then find the impedance during no load test. Impedance just voltage divided by current, right? So voltage equal to 1720 just now, 1270 divided by current 4.5 amp here. Current you don't need to divide by 3 because this is a line current equal to phase current. So phase voltage divided by phase current equal to this impedance, you call it Z impedance. And then find the R no load during no load test, which is 1000 just now. 1600 divided by 3I squared lah. 4.5 M squared multiplied by 3. 16,000 ni divided by 3 mean per fasa lah. 1600 divided by 3 got per phase. No load divided by 3. You got per phase divided by this current. You got this R no load. We call it this R no load. The resistance during no load. So we got the Z no load. We got the R no load. So the square root 2 Z squared over minus R squared. Then you got the X total at no load. So this one equal to 281 equal to S1 plus SM. S1 plus SM. Tengok letak dia kan. If you see this circuit just now, you remember? Here. And the impedance is S1 plus SM. For no load. That means S no load equal to S1 plus SM lah. Because of this circuit. So S1 plus SM equal to how much? 280.0 ohm. Okay, this is not complete yet. Just on the we have done on the no load test. Now we go to the block auto test. Go to the second part, block auto test, which is this one. Alright. So for block auto test, we know the power just now how much? 9,000 watts consumed by the machine. 9,000 watt. So you can find the RBL per phase. RBL block rotor per phase. So 9,000 divided by 3, you got per phase power divided by 25 amp squared. Because current now is 25 amp flow. Here is 25 ampere. Then you got the RBL per phase. So which is equal to this resistance 4 point equal to, if you see the circuit just now. Here. What is the resistance here? R1 and R2. R1 and R2. That means RBL equal to R1 plus R2. For the resistance, right? So R1 equal to RBL. R1 plus R2 equal to RBL. R2 equal to RBL minus R1 lah. Then you got the resistance for the rotor winding 2 ohm. So that is a function of the block auto test. We can calculate, we can determine the resistance of rotor. Okay, fine. Okay, now we go for the impedance now. So we do testing at 15 Hz, right? Here you mentioned here in the testing, frequency is 15 Hz. 15 Hz, then we need to find the ZBL, total impedance. So we divide by I1. So 270 is a line voltage. It's line voltage divided by Z3 give you phase voltage. Divided by current, you got 1.64. This is ZBL. Right? And then you can find XBL, the impedance during block auto test, which is ZBL squared minus RBL squared. And square root 2 of this. You can have this 3.98, this XBL. At 15 hertz. So this impedance we obtain at 15 hertz. So if we want to change to 60 hertz, then because the no load test will based on 60 hertz, but block rotor test will based on 15 hertz. That means you need to standardize lah. Everything must be same frequency. So this 50 hertz you need to change back to the 60 hertz. That means you have to do this conversion only. So 3.98 ohm in 60 hertz equal to multiply by 60 divided by 15. This is a conversion ratio dia lah. So this one equivalent to 19.92 ohm in 60 hertz. So if we do test in 60 hertz, we got this component 15.92 ohm. Conversion only. So this one equal to S1 plus S2. See that what is impedance there? S1, S2. The reactance, reactant S1 and S2 in series. So S1 plus S2 equal to this reactant, which is 19.92. And basically S1 equal to S2 lah. Basically, we say that S1 equal to S2, so we can divide by 2. Then we got the 7.98. That gives the S1. So once we get S1, we can calculate SM. Because SM from here, SM equal to, you see that's one just now previous. Here. S1. You know the S1 already. We know the S1 already. So we can find the SM. So SM you just come from this value lah just now. Yeah, S no load here. S no load equal to 281 equal to S1 plus SM. So we found S1 already, so we can find the SM from this equation. So we got SM which is 273.04. Then we can construct the circuit of the IEEE, but here it's not shown. I missed the slide lah. You can draw your own lah. You just draw your own. So now our induction motor have complete parameters. We have complete parameter already. Here you can draw your own lah. Here you can put R1, S1, S2, SR2 over S, SM based on IEEE or based on discrete, doesn't matter lah. But we have complete the parameter of induction machine per phase. So that's okay. Now our job just to find the performance machine, performance parameter. So once you got this one. Alright. Ada soalan? That's how we calculate the component for the induction machine based on testing that we did in the lab lah. We did the no load test and also block auto test. What is it? Just go to this slide. I think we touched already before. We touched already lah. This one no need to change. P mechanical equal to torque mechanical multiplied by speed mechanical. They use mechanical speed. Before that we use omega R. Same thing lah. Omega R, omega M. You know this mechanical speed equal to PM equal to this formula lah. I2 squared multiplied by this impedance. And then, okay, this also can be represented by this one. I can skip this slide. Same thing only before. What is this? Okay, this also can be represented for our machine just now. But in this example, we have RC or RM. When we want to show some performance calculation here. Okay, this induction motor couldn't scale also, but we still keep the RM there. We just follow this slide only. Maybe it's useful for us. Okay, so based on this parameter circuit or equivalent circuit, we know the V in first. The power that we apply to the machine equal to V line, I line, V phase, I phase, cosine theta multiplied by 3. This is the total power to the machine. Or you can use 3, square root 3, V line, I line, cos theta. You get the same answer lah. This is the total power to the machine. Okay. So the total power equal to P in somewhere there. Input here is the power come from utility equal to. If you say V phase, that means you have to multiply by 3. If you say V line, then insert 3 V line, I line, cos theta. So you must differentiate within this one. If multiply by 3, that means we want V phase lah. V phase, I phase, cosine theta, multiply by 3. This is input. Okay, now you got R1. R1 represents just now stator copper loss. I1 means 3 I1 squared R1. You got one losses there, stator copper loss. When you got core loss there, RM. Normally in our example later on, we just embedded RC RM links in the mechanical loss, so it won't appear here lah. But here doesn't matter lah. I just follow this slide on this. So if you want to calculate the core loss, provided they give you the component RC or RM, you can find that. So V squared over RM divided by 3, you got the core loss there. Okay, core loss. So P gap, PA gap, PAG or PG sama lah. PAG or PG same thing lah. So PG equal to I2 squared multiplied by R2 over S multiplied by 3. Sama tadi kan, same formula, same thing. PAG is air gap power. The power that we transmit from the stator to rotor through air gap. Equal to P in minus these two losses. P in minus losses across stator and losses across RM equal to PAG lah. Same thing. So P in minus losses across stator minus losses across RM or core. That give the PAG. Copper loss here. You know this component, this component can be divided by 2, right? R2 over S ni can divided by R2 plus the other one is a mechanical power. So you want to find the copper loss, just this formula only. Or P2. Tadi kita pakai P2 symbol dia. This one you pakai PLR. Doesn't matter. The symbol dia is up to you. As long as you know what you write there, okay, fine. I2 squared R2 represent the copper loss multiplied by 3, total copper loss. At the rotor side. When you talk about I2, it represent the rotor side. Okay, P mechanical. P mechanical is PAG minus what? P2 lah. PAG minus P2. P2 ni or PLR sama lah. PAG tolak P2 or PLR give you the P mechanical. So if you derive this one, you get the same formula like we did before. Same thing. That means this one minus PAG, this formula, minus this formula, you got 3, same like we did before lah. Equal to PAG 1 minus S. So just ding dong, same thing only lah. P shaft. P shaft ni net power. P shaft is PM minus P rotational. P mechanical, gross mechanical power ni minus rotational power tadi yang you create tadi kan. Tadi you just calculate just now P rotational. Based on no load test, you can find P rotational. So if you know PM minus P rotational, you got the P shaft. P shaft net power lah. So P shaft divided by P in ni P in P in. So P shaft divided P in give you the efficiency of the machine. Kecekapan dia. How much efficiency dia? Just P shaft divided by P in. Okay, P in, this formula P in lah. 3V phase I phase cos theta. P in. And the P shaft, P mechanical minus P rotational. So P shaft divided P in give the efficiency of the induction motor. Okay, torque, develop torque. Torque is equal to P mechanical divided by mechanical speed. P mechanical, you have this one, this formula for mechanical divided by the mechanical speed. PM, omega M lah. Omega M itu 1 minus S omega S kan. 1 minus S omega S that give the omega. The same if you want to represent in omega S lah, you can put like that. Okay, so the torque can be shown by Pn over P omega M. Pn divided by omega M, you got this one. And then we know that this relationship lah, omega M equal to 1 minus S omega S. Then we can have the torque equation like that lah. Which equal to PAG, this is PAG lah. I2 squared over R2 is PAG over omega S. Same lah. Like we did before lah. So torque equal to 3 PAG divided by omega S. Or 3 omega M. 3 omega M pula. 3 boleh. PAG. 3 PAG divided by omega S. Or 3 PM divided by omega M. This is PM, mechanical power. 3 PM divided by omega M. Or 3 PAG this PAG divided by omega S. Okay. Or torque also can be represented by this one in terms of respect to omega E. So ada tiga formula for torque lah. First, with respect to omega M, which is rotor speed. Also can be represented by omega S, which is synchronous speed. Also can be represented by omega E, which is supply frequency. Ada tiga lah. So three possibility that we can use to calculate motor torque. Up to you lah. But normally this is the common one lah. We use this formula. The most common one we use with respect to aggregate power divided by omega S. Okay, this is a common formula lah. We need to drive torque. Itu PAG. This is a PAG divided by omega S. It's common one. Also you can use the you don't like this one. You like the other formula. You can use this one, which is PM, P mechanical. P mechanical ni is this formula. So PM divided by omega M. 3 just to show you the total power, total torque only. If you remove number 3, then that means torque per fasa je lah. If you multiply by 3, total torque. So that don't get a bit confusing lah. 3 represent total torque. Alright, or you can represent by this one lah. Ini apa ni? This is I2 squared R2 over S represent what? Represent the PAG. Okay, so PAG divided by P. P PAG divided omega E. P PAG divided omega E multiplied by 3. That also give you the electromagnetic torque for the machine. So there are many ways to present torque. But the most general one lah, this one lah, kita pakai formula ni itu PAG divided omega S. The rest sama je, you cuma tukar-tukar, you just change the style only lah. Ada soalan? Anything that you want to ask so far? Ada? Yalah, kalau ada, if you do in the class senang kan, you can do your exercise, but at home I ask you to do the exercise, nobody do the exercise kan. So the time has to go like this lah. Kalau dekat kelas kita boleh delay the time. You can do your own exercise. I can check. Right? So the content of syllabus tu will be slower lah. Kan? But this one can be more faster lah. Okay, tak apa. Kalau if you have some problem with this contents or lecture and not very clear, and so you can interrupt lah. Just interrupt lah. Okay, without interruption, I assume you understand lah. That's it. Okay. Nak tahu tak tahu, you understand tak understand after test kan baru tahu lah. So kalau tak ada test, tak ada quiz, you don't know lah. I assume everything understand lah. Alright, so this example, next example lah. So we have this circuit now. This basically is a IEEE circuit lah. It's IEEE circuit with data given lah. With all the parameter given there. We just read this example, the sentence. A single phase, I think it shouldn't be single phase. It should be per phase. Single phase and per phase is different things, right? Per fasa. Because motor can be single phase motor, it can be 3-phase motor. Single phase motor is totally different with the 3-phase motor. So I think the best phase should be a per phase lah. It should not be single phase. Later on we have to change this one. It should be per phase. Okay, you cannot use single phase. A per phase equivalent circuit of a 6-pole SCIM, square cage induction motor that operates from 220 volt line voltage at 60 Hz is given below. Okay. Calculate the stator current, input power factor, output power, torque, and efficiency at slip of 2.5%. The fixed winding and friction losses is 350 watts. Neglect core loss. Neglect core loss means RM is removed from here lah. Previously we got RM, right? You see RM just now here, RM. When you see neglect, you remove this from the circuit. Even you don't put that, sometimes you just embed it to the rotational loss. Doesn't matter lah, that's only it. The fixed winding and friction losses is 350 watts. Neglect core loss. Calculate also the starting current. Okay, jadi first we solve the problem with the slip of 2.5%. Dia tak cakap lah sini, is it rated slip or doesn't matter, they just put slip only. If they say rated slip, then they will give you the rated speed, right? But otherwise, we just use the 2.5% lah. So that means we need to solve the problem with slip 2.5%. So R2 over S there, I think they miss one there. You must put R2 over S here. Okay, here you must put R2 over S. Okay, R2 over S here, then X2, SM. Okay, they give different values as S1 and S2. Dia 0.2, 0.5. But normally we say same lah. But in the evaluation, we put different way lah so that you can calculate. SM R1. This is stator current. This is stator voltage. This is rotor current. Okay. The first find the per phase. So what is the per phase for the voltage? Okay. It not mention anything about the winding, but they assume here the system, the stator is star connected system. Okay, but it's not shown here. It's not written here. Because the solution there we divide by set 3, that means the system is the stator is star connected system. Because the star, then we divide by set 3. Then we got the voltage we want per phase. Okay. 1727. But in the question they didn't say anything about the winding topology, right? So but in the solution they divide by set 3. So we know that lah the stator is connected as star connected wire. 127 and slip to 5%, which is 0.025. Okay, clear? Alright, so we move one by one. First, find the stator current, I1. So what you got to do now? In order to find I1, this is like IEEE circuit. You just find the total impedance first. Total impedance. I mean, this one series, parallel, series. Okay, understand? But remember, for the X, you need to put J. It's an imaginary component. So JX1, JX2, JSM. If you're missing the J, then all your calculation will be wrong. Just be careful lah. Be careful. So ada inductor, ada J. Okay. So R2 series dengan JS2 and parallel dengan JSM, then series with this one. You have to do and add S equal to 0.025. Kat sini kena ada R2 over S lah. Don't miss. Sini it must be R2 over S. Ini lah dia buat lah. Okay, dia simplify lah. Dia dapat Z total lah. With X equal to 0.025, then you find the value of the Z in equal to 4.2. Impedance 20 degree. Z positive. That means we know lah. That means power factor must be cosine this angle lah. Lagging. Lagging. Kalau you punya load inductive, power factor dia lagging lah. That means I lagging current. I lagging voltage by cosine 20 degree. Ini basic thing about the electrical engineering lah. Kalau angle dia positif, that means the current is negative lah. Negative because the current lagging voltage. So the power factor is lagging. Okay, so Z to this value 4.2 angle 20 degree. Then you can find the current there. The current source current, total current. Di V divide by Z lah. V1 127 ni tadi divide by Z. Z in, you got the current. Now you see there, the current is 30 A with angle of negative 20 degree. That means I lagging voltage by 20 degree. That means the power factor is lagging lah. You know that. Cosine 20 degree lagging. Kalau inductor memang dia lagging lah. Kalau di capacitor dia leading. Okay, the current equal to this value. P in, power input there. How much P in? Formula dia lah tadi kita bincangkan. 3 V phase I phase. V phase I phase cosine theta. So V phase 137. Here we calculate already 127 there. I equal to 30. I you don't need to divide by 3 because this is star already. So just pakai 30 degree lah. Cosine theta, cosine 30 degree. Multiply 3 because it's total power. You got this power lah. Total power in. 9,758 watts. Right? Okay, P loss there. How much P loss here? R1. I squared R1 multiplied by 3. This is stator copper loss. Tolaklah. P stator copper loss just 3I1 squared R1. You multiply, dapat 140. And then PA gap. PA gap is the power that we transfer from the stator to the rotor equal to PE minus P stator copper loss. Dekat sini P core tak ada kan, kita neglect. Dia tak adalah, so kita tolak ni je. So PE minus this one, you got PAG. So PAG just PE minus P stator copper loss. This is a total lah, PAG. Kat sini pakai PG je. PG equal to PAG lah, benda yang sama. 10,216 watt. This is a PAG. Then from PAG, you can find the gross mechanical power, PM. PM equal to S. PM or P, dia pakai simbol P out. So, tadi kita pakai PM. Di sini pakai P out lah. PO. That is equal to PM lah. Same lah. Same thing ni. Previously we use PM, but in this slide we use P out. P out equal to PM lah in this case. The PM equal to 1 minus S PAG. Okay. PAG we know already here. 1 minus S we know already. Then you can find the PAG or PM or P out there. And P shaft. P shaft is P out or PM minus P rotational loss. 350 kan. There you go. P shaft net power lah. Generated by the machine. Then divide by input power, which is this one. Give you the efficiency of the machine. 89.3% only. Kecekapan dia. That means 10.7% is losses lah. Losses. The power from input tadi, 10.7 goes to losses. Only 89.3% used to drive the motor. Okay. Torque you boleh pakai tadi lah. Formula dia apa? PM divided by omega M. PM divided by omega M. Ataupun you boleh pakai PAG divided by omega S. Omega S ada lebih lagi tak omega S ni? Omega S itu 120F divided by P. Boleh kan? P dibagi. P is 6. 120F. Dia dapat cari jugalah. You can calculate the omega S also. Or you can use this formula. Omega M. Rotor speed. So ada 3 formula kat sini. In order to find torque, you can use 3 formula. Formula that we studied before. We can use this form. The first one, you can use this formula. Here. Torque equal to Pn divided by omega M. Or P out divided by omega M just now. Or you can use PAG. PAG divided by omega S. Or you can use this one. So all the formula that we use will give the same result, which is 78.4 Newton meter. Correct? Boleh? This is torque developed by this example lah. At slip 2.5%. Okay, so at this slip, this is a torque produced by the machine. This is the power produced by the machine. So now they say last one, they say here, what happen at starting? At starting, how much they ask you to calculate starting current. At slip 2.5, the current is just now how much? 30 ampere only. At low slip, you got 30 ampere. Now they ask you to find the starting current. So at starting, how much slip? Starting just now, we know that starting NR equal to 0. NR is not moving yet, equal to 0. So slip equal to 1. You go back to this one, this formula, this circuit. R2 over S equal to R2 over 1. That meaning by starting. And you do the same thing, get the Z in back. Find the Z total, Z in with S equal to 1. Calculate Z in first. Then based on this question, okay, you find the Z in, S equal to 1, then this is your Z in. How much? 0.76 now, very low impedance. At starting Z in very low, 0.76. That's why current very high. Here in the slip 2%, how much Z in just now you calculate? 4.2. 4.2. When slip 2.5%. But when slip equal to 1.76, very low impedance. So how much the current now? Phase current, 167, which is 5 times bigger than full load current. That is a characteristic of induction motor. Okay, starting current very high compared to the full load current. That's why you need to be careful lah. That's why dalam lab machine tadi, bila you start motor kan, you use the variax. Variax is a one method to control the starting current. That means instead of applying here 127 volt directly to the machine that's starting, you need to increase slowly, because when machine start to rotate, the current will go down. You cannot plug in directly 220 here lah. Here just put 220 volt. You cannot just plug in 220 volt or 415 volt, for example. That's why we need the starter to control the voltage, to control the starting current. We can see the difference when you apply directly 170 volt ni, 127 volt, you can get the current is about 167 ampere, very big current compared to the 30 ampere here, which is rated current. So be careful lah. Be careful so that you don't spoil your machine. If the current flow too high, it will burn the wires. The wires will be burning lah. So your machine will be died. Will be dead already. Will die already. So be careful lah for the 3-phase induction motor. Alright. Ada soalan?